Alright, let's do it. Well, you shouldn't be surprised that there are several algebraically equivalent ways to do this. I'm just going to go ahead and this time distribute this 1 over n times this binomial. Next, I'll distribute the summation sign. And then remember that the only variable here changing is I. I is first 1, and then I is 2, and then I is 3. This n never changes. It's a fixed number. Maybe it's 10, maybe it's 4 billion. It's not a variable though. I is what's changing. And therefore, 8 over n squared is just a factor. And so is 3 over n. So we can rewrite these expressions like this. And now we can apply our formulas for the summation as I goes from 1 to n of I and also of a constant. The sum of the first n positive integers is this black expression. And if we add 1 to itself n times, we'll have n. Alright, what does this simplify to? That's clearly just 3, and here the 2 divides into 8 4 times, and this is n squared plus n. So 4 times n squared plus n is 4n squared plus 4n. And we can rewrite this maybe one more time to make it really, really clear. We can break up this fraction, decompose it into some components, simplify the n squared over n squared, and n divided by n squared. And now, as n approaches infinity, we have 4 plus 0 plus 3. So that gives us our answer of 7, which is choice C. Alright, I hope that made good sense. Now, I'm going to go ahead and go a little further than this and challenge you. Can you see this problem as a sum of rectangles? I'm going to review that idea. It's a pretty important one in integral calculus. We'll review that on the next slide. We're adding up a bunch of products. This blue part multiplied by the red part, and this stays the same every time. So that will be the fixed width of each rectangle. This must be the height. Ask yourself, what would the f of x function be here? We should be able to discern from this expression that this is going to basically be the definite integral from 0 to 1. How do we know that? We know that the width of each individual rectangle is going to be the length of that interval, that width of the interval, divided by the number of rectangles. Again, the width of each individual rectangle, and there are n rectangles, will be the total width of that interval from A to B, say, divided by the number of rectangles. So that total width of x values is 1. Alright, well, how do we know it's from 0 to 1 and not from 1 to 2? We can tell that by using this expression. The only thing that's changing in this expression is the input inside of parentheses. So that must be our x value. And when I is equal to 1, that's where we start with an x value of 1 over n. I think this will really clarify it. If the width of those x values was 1, but not going from 0 to 1, instead going from 1 to 2, then that first rectangle, when I is 1, would have needed to have an x value to get our height of 1 plus the width. It would have looked like this. Since we are not starting at some beginning x value like 1 plus the width to get this x value to get the height of a rectangle, it must be that this value right here is 0. 0 plus I over n. So we're actually starting over here. So each rectangle is a width of 1 over n. And to find this rectangle's height when I is 2 for the second rectangle, to get its height, it would be 0 plus the width 1 over n plus 1 over n, or 0 plus 1 over n twice. Or just 1 over n twice, which is what's highlighted in yellow. When I is 2, that'd be 2 over n. All right, so if we can discern that, and you get good at it with practice and by thinking about this and really understanding it well, if you can discern all that, then we can determine that this is equal to 7 a lot faster than the way we did it on the last slide, because it's just going to be the area of this trapezoid. And we all know that this is the area formula for a trapezoid, and the height is the distance between bases, and the bases are the parallel sides. So this is a base and this is a base, which means the height, the distance from one base to the other base, is 1. And the bases are the lengths of these parallel segments. This base was 3 units long. The vertical intercept was 3, so this is the point 0.03. And this base, when x is 1, is 11 units long. And there's our 7 square units. So if you can conceptually connect this to the sums of rectangles from 0 to 1, when the heights of the rectangles are determined by 8x plus 3, then we can see very quickly that it's just a trapezoid and find the area without using all of those I formulas. All right, you might also be thinking, couldn't we also have done the definite integral from 0 to 1 of 8x plus 3 dx? And yeah, you could have done that too, but we didn't review any of that yet. You'll get 7 there as well. All right, I hope this was helpful.